Alright, today we're going to learn about the periodic trends. The first one we're going to start with is atomic radius, which is directly related to how big an atom actually is. So first, give you the definition of atomic radius. Radius is half the distance between bonded identical adjacent atoms. So essentially the distance from the inner part of the nucleus to the outermost part of the electron cloud. Forgot my marker. Here we go. When we look at the trend observed on the periodic table, each element has different components and therefore is going to have a different size. The trends that you can observe is that the smallest elements are at the top right of the periodic table and the largest elements are at the bottom of the left. So this implies two trends. As you go from left to right across the periodic table, the elements get smaller, and as you go down, they get bigger. Now we're going to explain why each of these two trends is observed. One, as you go down on the periodic table, what's going to happen is each row incorporates a new energy level or a new shell. And if you think of it like you would Russian dolls, you start off with something really small, and each shell you add increases the size, that explains the trend going down. It also increases the amount of shielding, which is something we're going to get to in the next slide. As you go from left to right across the periodic table, the elements get smaller. And what's happening is you have the same number of electron shells, which is going to result in the same amount of shielding, but each element has one more proton than the element that came before it, resulting in a stronger pull and attracting the electrons closer to the nucleus, making the atoms smaller as you go from left to right. So right now I want to talk a little bit about shielding. Shielding is the repulsion of outer electrons by inner shell electrons. And I just wanted to show this visual because it shows that the distance between the electrons, and since their electrons are all negative, they're going to repel each other. The inner shell and the outer shell, they're actually not that far apart relative to how far apart the electrons in the outer shell would be to each other. So the shielding electrons or the inner shell electrons have a much bigger impact on how far out they repel the outer electrons. And this is all related to Coulomb's law, which states that the force of attraction, or repulsion if they're like charges, is proportional to the positive charge times the negative charge divided by the distance squared. What this basically implies is that the force of attraction or repulsion drops off with the square of the distance. And so effective nuclear charge takes into account two things. It takes into account the shielding, which negatively impacts the effective nuclear charge, and it also takes into account the number of protons in the nucleus, which is going to have a positive impact on attracting the electrons as you go across a row. And you can see if you look at the effective nuclear charge observed by the elements in the second period, you notice a trend where lithium has the least effective nuclear charge and fluorine would have the highest, and that explains why the electrons are drawn in more strongly in fluorine, resulting in a lower atomic radius. And you can see that visually here. As you go from left to right, the atoms get smaller because the effective nuclear charge increases. And then when you go down a row, it gets bigger just because of the amount of shells that you have incorporated. All right. Now, we know that metals like to lose electrons to become cations. So what this shows here is the gray atoms represent the elements in their neutral state. The colored, which are pink for the metals and blue for the nonmetals, represent their ionic state. So metals tend to lose electrons, and when they do that, they're going to get smaller. One, a lot of times they're losing an outer shell of electrons, which is going to make it condense. You also have less repulsion observed, and now you have a greater amount of positive charge than negative charge. It's going to pull the electrons in tighter. When you look at nonmetals, they tend to gain electrons to form anions, which are negative. You can see that they get much bigger. And this is completely related to the increased negative charge in the electron cloud, increasing the amount of repulsion. And you can see that oxygen goes from being 0.73, these are angstroms, I think, to 1.4. It almost doubles in size when it becomes a negative ion. So just showing how when atoms become charged, it impacts their size. So again, metals get smaller, nonmetals get bigger because of the increased repulsion. And again, when you go down a row on the periodic table, you're going to be adding shells. So it's still going to get bigger from top to bottom when you're looking at ions or you're looking at neutral atoms. Now, for atoms that are isoelectronic, what that means is they have the same number of electrons in their outer shell. These would all be isoelectronic. Oxygen is a -2 ion, has 8 electrons to begin with, gains 2, -2 charge. All of these have the electron configuration of neon. So magnesium is positive 2, sodium is plus 1, neon neutral, fluorine negative 1, and oxygen negative 2. And you can see that these ions and the neutral element neon all have different sizes, and it's completely related to how strong the nucleus is. The more protons you have in the nucleus with the same amount of repulsion from electrons, the closer together these electrons get pulled in, and the smaller the radius becomes.